So now we're going to go ahead and do some more questions out of 2.8. Just so we can work out and get through a lot of these, I'm going to get to the equation, and you can finish it on your own if you want to. Because solving them is generally not where we struggle. We struggle in the setup. So before break, we did 28. Let's try to see if we can set up 29. It's very similar. It is just a little bit different though. Bless you. So 28. Or sorry, 29. So an artist invests in a mutual fund account that pays 6%. And 6,000 more than 3 times as much in a mutual fund paying 5%. Her total annual interest income from the investments is $825. How much does she invest at each rate? So let's see what we're working with here. Well, we've got these two accounts. So we're going to use dollar signs to represent those. And remember, each of these has an amount and a percentage rate that it pays out. This is question 29 here. One and two, and those add together to give you a total amount. And we have an amount in each account and a percentage rate that they pay out. Okay, so let's take our time, make sure we see where these numbers are coming from. An artist invests in a mutual fund account paying 6%. So from that little piece there, what do we know? We know that the percentage rate is 6%. Do we know how much is in that 6% account at all? No. Okay, so that's going to be our unknown. So that's going here, and that's our X. We're going to take this money, and we're also going to add some more money in a different account. And it says, and 6,000 more than 3 times the amount. So 6,000 more than 3 times that amount would be 3x plus the 6,000. And that fund pays a little bit less. That fund only now pays 5%. And we'll go ahead and add these across to get the total amount. Not the interest, this is total amount. And my total amount would be 4x plus 6,000 if I add across. Now we work with our interest, right? In mixtures, you would use a pure. In investments, we use interest. And your interest is the amount times, again, the percentage rate. So our first one. Always be very, very careful with these percentages. It's easy to miss these and not use enough zeros. So 6%. 6% is not 0.6, it's 0.06. And then we're going to have to multiply it by x, by the variable x. And then our second mutual fund, it pays 5%. So that's 0.05. And how much is in there? 3x plus our 6,000. And then what goes on the right-hand side? What's going to go on the right-hand side is the total interest. And how much total interest did we make? We made a total of $825. I think you can finish it from there if you want to. You don't have to, but I'm just working out and setting up examples. It's the setup where we struggle at, not so much solving. Solving takes longer, but we already know how to do that. So I'm not spending a lot of time solving these. I'm just setting them up. Question 30. Okay, so question 30. With income earned by selling the rights to his life story, an actor invests some of the money at 3% and $30,000 more than twice this amount at 4%. The total annual interest earned from the investments is $5,600. How much did he put in each rate? Very, very similar again to the previous one. Set it up the same way. We've got 1 and we've got 2. And these go together to give us our total amount. We've got amount and percentage rate. We're going to take our time to make sure we see where all the pieces go. So with an income earned by selling the rights to his story, an actor invests some money at 3%. Okay, so some money at 3%. So we don't know the amount. That's going to be X. The percentage rate is 3%. Is everyone okay with that? Now we look at the next piece. And it says $30,000 more than twice that amount. So $30,000 more than twice that amount. So twice that amount would be 2x, and then we're going to add that $30,000. Okay, and what percentage is that? Well, that is going to be a 4% account. And we always add these across. So when we add these across, we get 3x plus our 30,000. We never really use this, but I don't want you to start putting that 5,600 there, because that's not the total amount of money. That's how much money you made. You might have $100,000 in that account, but you're only going to make 5,600. So they're big differences. So that's why I always just have you add across and put it there, because otherwise you'll be putting the number in the wrong place. Now we're going to build our equation off of the interest. And that's the amount times, again, the percentage rate. So the first one is 3%. So that's 0.03. And how much is in there? Unknown amount, X. Is everyone okay with that? Now we repeat the process again for our second one. Percentage rate is 4%. So 0.04. How much is in there? 2x plus your 30,000. Those go together and give you a total interest. And from the question, it tells you that that total interest is $5,600. And if you want to, you can finish it from here. We're more concerned, though, right now about the setup, because we always struggle with how to set these up. now let's look at a little bit different, same type of problem, just a little bit different one though. Let's look now at question 35. It's a little bit different, but it's very, very similar. In January of 2017, U.S. first-class mail rates increased to 49 cents for the first ounce and 21 cents for each additional ounce. If Sabrina spent $16.45 for a total of 45 stamps of these two denominations, how many stamps of each denomination did she buy? So we're looking at some stamps here. And we're going to set it up in a very, very similar manner. To what we worked with earlier. But we're working with stamps, so we're going to call this the number of stamps and the denomination of those stamps. Okay, the worth of the stamps. So when we read this question, what do we have? We've got two types of stamps. We've got the 49-cent stamps, and we've also got, so that's part one, 49-cent stamps. So their denomination is 49 cents. We've also got the 21-cent stamps. So that's 0.21. Now, just like before, these are going to add together again. And what do we know? Okay, well, when we read it, it says we got $16.45, and we have a total of 49 stamps. So we need to come up with our total. So this is going to be our total stamps over here. So we have a total of 45 stamps. Now, do we know how many 49-cent stamps we have? Does it tell us in this question at all? No, we don't know. So if we don't know how many 49-cent stamps we have, we use the variable x. Now, we also don't know how many 21-cent stamps we have. We did one of these earlier. And if we don't know the value of either one, we call the first one x, and the second one is the total minus x. Remember that? So this one then would be 45 minus x then. Because we know we have a total of 45 stamps, because that's what we're looking at. Now we can go ahead and build our equation, and we're going to look at our value. And the value is going to be the number of stamps times the denomination. So very, very similar to what we've done. Just a little bit different. We call it stamps instead of an amount. And denomination instead of interest rate. So what do we have on the first one? Well, the first one, we've got stamps that are worth 49 cents. So that's 0.49. And we don't know how many of those we have, so we have x. And then we're going to also get some 21-cent stamps. And those stamps are worth 21 cents, so that's 0.21. And how much is in there? 45 minus X. And how much is the total value of all the stamps put together? Well, the total value of all the stamps put together is how much we spent. And we spent $16.45. Okay, and I want you to go ahead and try that one later on your own. I'm not going to work it out because it takes so long to work these out. I would rather us spend the time setting them up. That's where we struggle. That's what we're going to do. Set these up. $36 is very similar. A little bit different. Only difference is in the labeling. A movie theater has two ticket prices. $8 tickets for adults, $5 tickets for children. If the box office took in $4,116 from the sale of 600 tickets, how many tickets of each type were sold? Okay, so we're going to label it instead of stamps. In this case, it's tickets. And you can call it denomination, you can call it cost of the tickets, whatever you want. We'll go ahead and just be consistent, call this denominations. Okay. And then over here, we of course have our total tickets. Not the cost, the total number of tickets. So we always have to make sure we label things because we don't want the cost yet, we want the tickets. So we're going to the movies, and there's two ticket prices. We've got $8 adult tickets. We don't know how many adult tickets we have. It doesn't tell us. We don't know. We don't know, so what do we use? We use an X. Then we've got some other tickets for children, and they're cheaper. So they only cost $5. So we're going to go over here with the 5. And we don't know how many children tickets we have. So we're going to leave that blank for a moment. But we do know that we sold a total of 600 tickets. So there's our total number of tickets. And we should know what's going to go in this box. That box is our second unknown, and that's always going to be the total minus X. And how many total tickets do we have? 600. So that's going to be 600 minus X. Now we're going to look at the value of the tickets. And the value is going to be the number of tickets times the denomination. And our first one here. Tickets cost for adults $8. So that's 8x. Children tickets are a little bit cheaper. Child tickets. They are $5. And how many of those do we have? Well, we look. It's going to be 600 minus x. And then on the right-hand side, we need the total amount or total value of all the tickets put together. Well, the total value of all the tickets put together is 4116. So 4,116. And we've set that up. You should know how to finish it. Finish it. Find the two number of tickets. $38. We'll do one more of these before we move on to the distance questions. A customer at Harriet's coffee shop wants to buy Italian espresso beans and Kona Deluxe beans. If he wants 4 times as much of the Kona Deluxe as the Italian espresso, how much of each can he buy for a total of $247.50? And our prices are listed on the sign over here. So we're only going to be concerned with our Kona Deluxe and our Italian espresso. Let's go ahead and look at this one. And we're working with coffee, and this coffee has a weight of pounds. So we're gonna label our amount pounds. And just so you know where these came from, we've got espresso, and that Kona Deluxe. Espresso and Kona, and we've got now number of pounds, and we can look at, you can call it cost, value, whatever you like. We'll just use denomination again. We're used to using that. You could certainly use cost if you wanted, whatever you want to label it here. Okay, so we've got espresso, and that espresso is going to cost $9 a pound, and the Kona costs $11.50 a pound. And this is going to be the total number of pounds here. Okay. So we're going to buy these pounds, and if he wants 4 times as much of the Kona as the Italian Express. So we don't know the number of pounds of Italian espresso. So that's going to be the X there. And the Kona, we want 4 times as much, so that's going to be 4X, right? That's 4 times as much, so that's going to be 4X there. Adding them together, total number of pounds is 5X. Now we'll look at our value. And the value of all this coffee is going to be the number of pounds times the denomination. And you could use cost here, you could use whatever you want. I'm just using denomination because I've used it before, and I think it's less confusing to keep with the same label. But you could certainly write cost there. What's our equation look like? Well, we've got our espresso, which is our first one here. And that's 9X. And then we've got our Kona Deluxe. And that is 1150 times that 4X. And this over here is the total value of all the coffee put together. And what's the total value of all the coffees put together? We spent a total of We're on 38. We spent a total of $247.50. And again, you can finish it later if you want to. I am focusing right now on the setup. Now we're going to look at distance problems. And when we talk about distance problems, there can be three different outcomes. They can add together, they can subtract from each other, or they can equal. So on these, we have to draw a picture first to figure out if it's addition, subtraction, or if they equal. So this is specifically for distance. Now, if they go towards each other with arrows, these are called vectors, by the way. If they go towards each other like this, it's addition. If they go away from each other like this, it's addition. If one goes north, one goes south, that's addition. So those are all addition. If they overlap, it's subtraction. And so if they overlap like running a race, if they overlap, we've got to subtract them from each other. Or it might be something like this, where one's going north and another train's going north. That would be subtraction. If they overlap, they cross each other, that is subtraction. And they can equal when they are the same, like this one. Now this would be like, for example, driving to school and driving back home. If it's 10 miles to school, it'll be 10 miles back home. They're going to be the same. So these are our three different scenarios: addition, subtraction, or equals. The distance ones are actually quite a bit easier to solve. There's not as much to them. They're usually a lot easier to set up as long as you're careful with the vectors, the directions. But they're actually easier to set up and solve. Students struggle more with the investment and the mixtures than any others. Usually it's not such a big deal for the distance ones. When we drive a car, we've got three things that are involved. How long it takes us to get to our destination. Okay, we all know that. So if you're driving to school, you've got three things that are going to go on. Okay, how long does it take you to get there? How fast am I going? Rate of speed. And how many miles is it? So rate, time, distance. Those are the three components. Now, distance is calculated, and distance is the rate times the time. It's like the interest. So it's done the same way. And the period, done the same way. And the value, done the same way. These are not going to take us long to solve. $47, and we should be able to do several of these. From a point on a straight road, Marco and Chelsea ride bicycles in the same direction. Marco rides at 10, Chelsea rides at 12. In how many hours will they be? 15 miles apart. So there's some key words here. One of them is they're going in the same direction. So they're going in the same direction. And we've got these two people going in the same direction. And we've got a rate, a time, and a distance. This is on page 180. And we're looking at question 47. And I always like to write the faster person on top. So Marco rides at 10. Chelsea rides at 12. So they're going the same direction, so it's going to look like this. And this is going to be Chelsea because she's the faster one. Marco's down here. And each of these has a rate and a time. Okay, so Marco goes at 10, so his rate of speed is going to be 10. And Chelsea is faster at 12. And for the time, well, it gives us a time, and that time, in our case, is the number 15. Because it says, well, wait a minute, make sure we got it right here. In how many hours will they be 15 miles apart? So, sorry about that. That was my mix-up. When we talk about the time, well, we don't know how long they're riding for. So that's going to be unknown, but we do know that they have to be the same. Because they start at the same time, so they're going to be the same. So I don't know either one of these times, so I'm going to call these times x. Now these overlap. So see how I drew the vectors? See how they overlap? So since they overlap, they're going to subtract. Now, we build our distance just like we did our interest and our period. And your distance is the rate times the time. And we've got our two bikers here. We've got Chelsea. And we've got Marco. And what are we going to have to do? Subtract them. Just like we've done before. These multiply together. Rate times time. Chelsea is 12x. Marco, what about him? Rate times time. That's 10x. And how far apart do we want them to be? We want them to be 15. And this is our miles apart. So this is going to be 15 miles apart here. Very, very easy to solve. Add those together. That gives you 2x equals now 15. Right, we can divide by our 2. And that leaves you then with, what, 7.5, right? Or 7.5. So if we divide it out, that's 7.5. And what is that? 7 hours and 30 minutes. So that time is going to now be 7 hours, 30 minutes. I would accept either one. So you could write this as 7 hours and 30 minutes. That's fine. Or you could write this out as 7.5 hours. Either way is fine. I'll take hours and minutes, or I'll take it as a decimal. But either one is fine. So it should take them about 7 hours and 30 minutes to end up being 15 miles apart. Question 49. Question 49 has a table. We don't need the table. The table is just confusing. The textbook teaches with a table, but I found students get confused by the table. So don't even think about the table. We're going to draw our diagram. We're going to label it, and we're going to solve it. So Atlanta and Cincinnati are 440 miles apart. John leaves Cincinnati, traveling towards Atlanta at 60. And Pat leaves Atlanta at the same time, traveling towards Cincinnati in her antique car, averaging 28 miles an hour. How long will it take them to meet? So here's our picture. Now, looking at the picture, these don't overlap, do they? Right? They're going towards each other. So this is going to be an addition problem. So we're going to draw our picture, and we're going to label it. And this is John over here, and Pat. Now they're going towards each other. They do not overlap, so that's going to be addition. Each of these has a rate of speed and a time. So John leaves Cincinnati to go to Atlanta, and he's going at 60 miles an hour. So his rate is going to be 60. And do we know how long he's driving for? No. Doesn't tell us at all, does it? Doesn't tell us how many minutes or hours. We don't know, so we're going to use an X. Much easier to set up. What about Pat? Pat's traveling slower, 28 miles an hour. Pat's time is not known either, so it's also X. Now we can make our equation off of the distance. And the distance again is the rate times the time. Rate times time gives you that distance. So what's John's going to be? Multiplying those together, 60x. They're going to add because they're going towards each other, opposite directions. What about Pat? Pat is 28x. And then what's the total distance apart? Yep, and it's 45, isn't it? No, 440. Sorry about that, 440. 440, and that's the total miles apart. So now we can easily and quickly solve this one. So we'll add those together. So 60 and 28, that gives you 88x equals that 440. Divide by your 88. And that should leave you then with 5. So x is 5. So that means it's going to take them then 5 hours. So the distance ones are much, much easier to solve and work through. Not nearly as complicated. I want us to do one more of these, just to make sure we know how these are all going to work. Okay, so we're going to do one more. Let's look at 53. Okay, so question 53. Try to set up this one. Work it out here. So 53 says 2 planes leave an airport at the same time. One goes east, and the other went west. So opposite directions. The eastbound airplane travels 150 miles per hour slower. They are 2,250 miles apart after the 3 hours. We need to find the rate of each airplane. So this one is a little bit different here. So we're going to have to try to find our distance again. It is a little bit different though. So we're going to first draw our pictures of these two airplanes. We've got a plane traveling east and a plane traveling west. And this is question 53. Okay, so it is a little bit different. Not much though. It's pretty close to what we've done before. The difference is going to be in the rates. So it says the eastbound airplane travels 150 miles per hour slower. So we don't know the rate of speed of the west airplane. So we're going to call that x because that's unknown. On the eastern airplane, it says it's slower by 150. So that's going to be x minus 150, right? Because it's slower by 150. Now we still need a rate and we need a time. And they give us the times in this case. Normally we have to find the time, but in this case they gave us the time, and it says the times are going to be 3 hours apart. So they're traveling for 3 hours, and that's our time. Now we can finish it, because again we're going to find our distance. And the distance is the rate times the time. And this will be our last question that we're going to go over. So let's go ahead and finish this one out, and this will be it for today. We're looking at our western airplane. And that's again distance, rate times the time. So that's going to be 3x. By the way, these are not overlapping. They're going in opposite directions, so they add. The only time they ever subtract is when they overlap. These do not overlap, so they do not subtract. And then we'll look at our eastern airplane. And it's 3 times x minus 150. And then we want them to be, reading our question here, 2,250 miles apart. So there's that. There's our equation. Because this is the total distance. And we can finish this one out. That is then 3x plus 3x minus, what is that, 450, I believe. Let me double check, though. 150 times 3 is, yep, minus 450. I always like to double check things, though. And that equals your 2250. We're going to go ahead and combine those together. So that makes it now 6x there, minus that 450. That equals 2250. We'll add on that 450 to each side. Almost got it. We now have 6x equals, adding those together, it gives you 2,700. Divide by our 6. And that leaves me then with x equaling 450. Now we need to make sure we answer the question, and we want to find the rate of speed of each airplane. So when we talk about the rate of speeds, we need to go back, okay, and the western airplane is x. So the western airplane rate of speed is x, so that's going to be 450 miles per hour for that one. And the eastern airplane, it's 150 less. So the eastern airplane or the east plane here, is going to be x minus 150. So that's 450 minus 150. And that gives you then 300 miles per hour. So you've got 450 miles per hour for the western airplane, 300 miles per hour for the eastern airplane. So that's going to finish our lecture for today. Now, what's our homework? Well, we only did one section, and it's going to take you a while to work through that section. And I know we're going to have a lot of questions. So your homework is just going to be 2.8, and you should be able to do them all. Next week, we're going to go over 2.8. 2.9 is a much, much quicker, simpler section. Review for our exam, and then our exam will be in 2 weeks. So next week, we'll be finishing up this chapter. Following week, we will be taking our second exam.